So now, so far in this course, we have been dealing with one finance problem, which is this bond pricing problem. And we saw that that already gave rise to so many interesting insights, both
Correct.
mathematically and computationally, and of course about finance. So let us introduce the second of our three finance objects that we are going to study in this course. And this is this idea of portfolio choice. So
Correct.
what we're going to do is first just go through a very simple illustration of a portfolio choice problem. And then we'll see several different techniques that comes up and some computational issues that come up, right? So
Correct.
the most simplest version is we have two assets, and the numbers we are going to be using just to make things concrete, we are going to put some numbers, but these are just illustrative numbers, right? They don't necessarily correspond to some stocks, although these are like realistic numbers. So you've got two assets. One is something we are going to call a safe asset. And what do we mean by a safe asset? Basically, we know its return for with certainty, right? So typically, you think of like maybe some particular government bonds, right? But here, just treat it as a safe asset. So let's imagine that this is something that is going to return us 5% with surety. And then you have a risky asset. Let's say this is a equity index. And why is it risky? Because its return is stochastic. So we don't know exactly what's going to be the return from holding this asset. But based on maybe some past data or some modeling, we have a rough idea. Let's say that this is going to give us expected return. So when we say E, we mean expected return of 12%, and standard deviation of return, which is 20%. So sigma stands for standard deviation. So this is asset B, the risky asset. So that's going to give us a 20% standard deviation. Okay. Now, the problem that we want to solve is that given these two assets, and suppose these are the only two assets, how are we going to divide our, let's say, the amount of money we have available for investing in different assets, right? So let's suppose that we decide to put a fraction called W safe in the safe asset and a fraction W risky in this risky asset, right? So what are some constraints that has to hold true? So because this is the total amount of money that we are putting in, and these are the fraction of money we are putting in our different assets, so this has to add up to 1, right? So the total, there's some portion we are going to put in the safe, the other portion we are going to put in the risky. And let's just say for now that these are between 0 and 1. So there are involving short selling where this they may not necessarily lie between 0 and 1, but for now let's just keep our life simple and let's say these are between 0 and 1. Now, yes.
Yeah, go ahead, Vikram.
So what it means is now that we have basically a portfolio where we have put a certain fraction in the safe asset and a certain fraction in the risky asset, and we can characterize the portfolio statistically, right? So we have some summary statistics. So for example, what's the expected return from our portfolio? So this is going to be the expected return from these two assets. So basically, because we have put a fraction W safe in the risky asset, remember this is a safe asset, this is giving us a return of RF. So that's why you have got W safe plus RF, and the remaining amount we have put in the risky asset. So that's going to give us this expected. This is the standard formula, right? Expectation of AX plus BY is A times expectation of X plus B times of X.
Correct.
The variance of this portfolio doesn't depend on the safe asset, right? Why? Because remember, the safe asset does not have does not vary, right?
Any variability, because it's a
Right.
constant. It has no uncertainty.
Exactly. So therefore, the variance is coming only from the risky asset, but because we have put maybe only a fraction in the risky asset, so this is going to be weighed by that fraction, right? So why do we have squares here? Basically, again, this is the formula that variance of constant plus AX is A square variance X, right? That's the formula that you should remember from your basic probability and statistics, and that's what we are using here. So these are two formulas. So, but this is so far only the constraint side. In order to solve this problem, we also need to understand what does the consumer or the person who is making this investment decision want, right? So typically, two characteristics that we have, and I think if we go to the next slide, it might be easier to see, is that, this is again like as a first approximation. Typically, investors like to make more money, right? In expectation, at least. But they don't necessarily like the risk. Of course, you have some people who like the risk, but for most of us, probably we want ideal for us is more money, less risk, right? So one way of capturing it very simply in our framework that we have been discussing is to kind of like have an objective function where if you like, what I'm trying to maximize, my utility or my value, depends on only these two factors, right? What is the expected risk of return of my portfolio, and what is the variance of the return of my portfolio. So typically I want to have higher, because I like more expected return. So this is entering in a positive direction. But because I dislike risk, it is entering in a negative direction. And this parameter lambda basically captures how much I dislike risk compared to how much I like return, right? So for example, a very high value of lambda would correspond to I really strongly dislike risk, right? And a low value of lambda would be like, I really like the return part only, right? So then just to kind of like, you can just put numbers. So lambda very close to 0 means that, I don't care about the risk. I just want to maximize my return. But lambda very high would mean that, I put a lot more weight on the variance part. So this is like a very simple kind of like thing. And just to again do our numerical calculation, simply just take lambda equal to 4 for now, but you can keep it lambda generally also, right? So what is the problem now? So the problem is we want to maximize this objective function subject to the constraint that we have seen. So this is the constraint optimization problem. And you may want to just pause here for a bit and think about how you might want to solve it. So Sorish, what would be, putting on your computational hat, what would be the most easiest way to go about solving this problem?
If I want to be really lazy, I would do some grid search. But
Okay.
before we jump into the computation part,
But what do you mean by the greed search? Maybe we can. Oh, you wanted to discuss something about the problem, or you want to discuss something about the solution?
something I just want to take a small detour.
Hmm.
Why we chose this number?
Hmm.
So this is just not a textbook problem. It is a carefully chosen number actually. So in India particularly, the if you see the repo rate is around 5%. So even if you keep your money in say SBI fixed deposit or SBI bonds, you will get only around 6% or something like that. So the repo rate is risk-free rate. That is why we chose around 5%. And if you look into the Nifty index, the annualized Nifty index gives a return for last about 20 years. It's giving us around 11 to 12%. And that is why we chose a 12%. And if you look into the annualized volatility, it is median volatility is around 20%. So that is why we chose these numbers. And in fact, if somebody do not want to be very lazy, one way they can park their money is some part they just invest in, say, government bonds, which will give them 5.5% of return, annual return. And some part they can just buy Nifty Junior or Nifty ETF, Nifty 50 ETFs. It or so that way, and they just forget about it. Okay. So now question is how much they should put into government bonds and how much they should put into Nifty ETF. So they in that way, so that this actually not a textbook problem. It is
Yeah, but
actually a
I was just
very
wondering,
much
how are these numbers going to, you know, age well in a few years' time, right? So if you're watching this, after several runnings of the course, then like,
right.
would these numbers then look like wondrous or like so poor for that time? It's an interesting thought experiment, right?
Yeah,
But
I don't know. I don't know. But yeah, I mean, there's a good point. But when we were preparing the slides, that time purposefully we chose, if you remember, we discussed that these are the numbers we should take. And I purposefully thought like, we should always give examples to the students, which is more close to the real life and not just cooked up. So this is not a cooked up example. This is a example, carefully thought out example, a simple example to understand the nitty gritty of the computational part as well as a real life enough where one can go and execute this kind of problem, the solution of this kind of problem.
Right. Speaking of solutions, so you were saying something about grid search.
Huh. So grid search, I was like, if I have to be really lazy, I can try some grid search kind of thing. Or one thing is, I mean, that is what the grid search is like. W has to be between 0 and 1. So what I will do, I will choose 100 values between 0 and 1, right? And for each of the like 0, 0.01, 0.02, 0.03, and that like each percentage. And then for each W, I will calculate this particular F, okay, which is I know the value of expected RB, I know the sigma B, I will just plug it in there. Lambda I will take 4, and for each W I will say I will, if I calculate W disk is say 0.01, 0.02, 0.03 up to 1, then obviously W save will be 1 minus W, and I will see where I will get a nice curve, this curve, right? And then I will see where the curve is peaking. Suppose the curve peaks at W equal to 0.44. So that means based on my risk appetite at lambda equal to 4, 44% of my asset I should put into risky, and rest of the asset I will put into uh, safe asset. For safe asset. So this is the simple implementation of the grid search method.
Right. Okay. Maybe then we can also look at like some, because the problem is simple enough, we can also look at some analytical solutions, right? So I think the
Correct.
first analytical solution is simply to do substitution. How
Correct.
would that work here? Because it's like, actually, if you think about it, although it seems like a constant optimization problem, here you are actually just choosing one variable, right? Which is this
Correct.
W, right? So then we can just replace out this W saved by 1 minus W. And this is, how did we get this? This is basically, we are expanding this expression for ERP that we got in terms of the returns from the risky and the safe asset. And the variance, remember, we had found the formula also, right? So we are just putting those here in the objective function. And now we see that we have a function which just depends on W, right? And this is something we know all how to solve, right? This is something
Correct.
even I learned in like class 11, 12, not just, when Shorish was doing this, right? So you just set F, the first order condition, F prime W equal to 0. And then the second order condition is also going to work out because this is a nice function, right? But particularly, it's a nice concave quadratic function. And if you do the algebra, which we encourage you to do, in fact, the whole exercise, we would also like you to do both on pen and paper and with computer in the way that Sodish was talking about. So if you set F prime W equal to 0, this RF is a constant, it drops out. This is the W times the constant. So the constant is here, ERB minus RF. And then this is a quadratic term. So this 2 will cancel out with the 2. That's why, by the way, we had that lambda by 2 in case you were thinking, why did we have that 2? So you end up getting this expression. And if you solve, you get a value for W star, right? Which is that it depends on ERB minus RF, which has a nice interpretation in finance, right? It's related to something called the equity premium, but let's not get into that. It depends on your risk appetite, so lambda, and it also depends on the variance of the return from the risky asset.
Correct.
Second derivative is negative, so that is the other condition that we know from high school math to check. And if you now put in the numbers that we have, so for example, remember sigma b was 0.2, so sigma b square is 0.04, and lambda we had said was 4. If you put in those values, you end up getting 0.4375. So which was pretty close to what Shori had suggested, maybe that you should get if you do that grid search or the rough grid search that we have, right? So basically, interpretation again, roughly 44% in the risky asset and 56% in the safe asset, right?
In the safe asset.
Right. So if you had done the plot, this should match the plot. Now, one thing is like roughly you got 44 here, you're getting 43.75%. So, I mean, one way of doing that is probably to make it the plot more finer, right? The grid. I think that is discussed in the next slide. that you can decide how fine a grid you want. So if you do, for example, 1,000 points, probably you would get that, right? So
Yeah. Yes.
so one question, Shorish, is that why kind of like why can't we just stick to the either the analytical method or the numerical method? Why is like both ways of
So,
looking at a circuit?
my experience, Vikram, is if you have an analytical method, you should go for it
Mhm.
because your computational cost is much less. And if you have to, implementing grid search method or any numerical method could be computationally very expensive.
Mhm.
Right. So if you have an analytical solution and you believe that solution is somewhat optimal, it has good properties, mathematical properties, you should go for analytical solution. And you should go for numerical solution only when you do not have an analytical solution. So
Right.
that is a rule of thumb I definitely always follow, and many of my colleagues also I have spoken to, they have told me the same, that rule of thumb is if you have analytical solution, go for it, and go for numerical solution only when you do not have a analytical solution.
Right, right. Because I think also, as we have discussed, there are several things that can go wrong whenever you are doing the numerical method also. I mean, just as there are several things that can go wrong when you are doing
For
analytical.
example, I will tell you. So here we are only handling one asset, a two asset, right?
Mhm.
So because it's a two asset, we are just with the one asset. So we are doing grid search on one dimension.
Mhm.
Grid search work very good in one dimension. But if I have instead of two asset, I have three asset, then I have to do the grid search on two dimension. If
Right,
I
right.
have
Simplex, right.
exactly. So the simplex get bigger, higher and higher dimension,
Mm.
and the complexity of the number of computation increases in cubic times. Like, you have 100 points in one dimension, 100 points in another dimension. So now you have 100 times 100, like
Mhm.
one almost 1 lakh points where you have to evaluate all the values. So
Right,
this is your computation explode,
right,
right? It will, like, it will take forever almost for a higher dimension.
right,
So, and that is why even if you go for a numerical, you have to use some finer numerical algorithms to
right,
estimate
right.
these methods, this final solution.
Right, right, right. So it's basically what knowing both the tools, right? Because sometimes the
Correct.
analytical solution also may not be able to be tractable, right? Then
Correct.
you
That
have
is
to learn what
possible.
to kind of
That is very
like.
much possible. The analytical solution is not giving you the optimal solution. And
Right,
that time means you have to find a solution. The optimal solution does not have an analytical solution,
right.
and you have to rely on numerical methods.
Right, right. So, I mean, let's just add one more analytical method to our toolkit using the same problem. So, this is the Lagrangian multiplier, which is the standard way of dealing with constraint optimization problems. So, here we have it basically in a cookbook procedure, assuming that you have actually seen this before. So, how would we do it? So, first step is to form the Lagrange multiplier. So if you remember, this is writing the first as the objective function, which was this. Uh, Basically, then you have minus mu, which is this new variable, the Lagrange multiplier, times this constraint that was there, right? W safe plus W risky minus 1. So remember, this was equal to 0. That was the constraint, right?
Mhm.
So after that, what we do, the next step is to take first order conditions. And this is basically taking the partial derivative of this Lagrangian multiplier with respect to the three variables that you have, W safe, W risky, and mu, and setting them all equal to 0. So again, if you do this, we have written down the final results. So you should do this on using pen and paper, but you end up getting this sort of expressions. And then you have basically three equations in three unknowns. So three unknowns being W risky, W safe, and mu. And if you solve that, you end up getting this expression at the end, which is again the same as we had found in method one, right? So then one question you might have is, okay, then why do we kind of like need to know two different methods if, if they give the same answer? the reason is Lagrange multiplier works if
In high
even if you've
dimension.
got more than two variables, right?
Correct.
So
So when we will be handling, say, 20 assets,
right,
that time first method will not work.
right. Method of substitution
The
will
method of
works only if you have
substitution will
one
not
variable,
work.
etc.
Correct.
Right,
So that time we have to work with the Lagrange multipliers.
right. So then therefore we can actually move on to the next slide, I think. So there are some things to understand about Lagrange multiplier. So as we mentioned, it works well when you have got more than two variables that you're choosing. But there are also deeper reasons, and this is, for example, this mu term that we introduced all of a sudden, you might be thinking, where did this come in? So that actually, if you take again like economics courses, that has like a very deep interpretation in terms of shadow price of the
Actually,
constraint.
Vikram, if you go back,
Yeah,
you when we got this part, and from here, this equation, we got a mu equal to RF. Right.
right.
So that gives a immediately mu is basically my risk-free rate. Right?
Right, right. But I think that is specific to this application. My point,
Correct,
I guess, is
correct.
like mu is like more generally the Lagrange multiplier. I mean, more generally in terms of optimization problem, it has a deeper, I guess,
Ex-
significance. But yes, I mean, yeah. So for go ahead with like what's the interpretation for this problem?
No, in this case, it is showing that a reasonable, uh, you know, reasonable risk appetite will be risk-free rate of return, right? RF. Mu is essentially giving me how much risk-free rate, risk appetite I have, and reasonable risk appetite would be around the risk-free rate of return, or maybe a little more, with kind of a create a risk-free rate of return as a baseline. And do I have more than that? Do I have less than that? So that is the idea. And with every finance problem, with every economics problem, turns out this mu has some kind of deep economic interpretation. So one of the major things, oftentimes it comes out as a sort of a expected average price. So mu gives a sense of what is the expected price of the product that you are thinking about. So here, risk-free rate is sort of a of the price of the capital. You can think of risk-free rate as the price of the capital if you are borrowing from the sovereign or borrowing from the Reserve Bank.
Yeah, I
So
think this has like a lot of deep interpretations, right? But I
yeah,
think at this point, probably the main thing we want the students to take away is that this is not an arbitrary value that was just introduced for
correct.
mathematical necessity. This actually has deep interpretations in economics and finance, and we'll probably come back to this again when we are
Again and
discussing
again, yes, we'll come
derivatives.
back to this again and
Right,
again.
right. So there's also a computational reason to kind of like go through this example only in week one. It's because you again kind of like notice that if you go back to the previous slide, we had this three equations and they were linear in these three unknowns that we had, right? So remember the three unknowns were mu, W risky, and W safe. And if you look at the first few, the three first order conditions, these were linear equations. So again, we see that these linear systems keep coming up, right? So we saw that when we were discussing yield conditioning, we see it when we have this Lagrange multipliers. And that is why we are going to, again, going to be spending quite a bit of time trying to understand linear systems and its implication for both from a finance and from a computational perspective next week, right? So if we go back now, so this is again, this combination of Lagrangian and linear algebra is a very useful machinery. So you have been introduced to Lagrangian. We'll come back to it in more details. Linear
Yeah,
algebra is something we'll look at next week, but we'll combine them again later to come back to this optimization, portfolio optimization
correct.
problem later in the course. So just a few more steps you can do before, even from this simple example, we can learn some useful insights and some useful habits, right? So one is this sensitivity analysis. So what does that mean? So remember, we have quite a few parameters in this problem, right? We have this lambda, we have this sigma b, we have this expectation of RB and RF. These are like numbers that we took as given. We had some illustrative numbers, but we can do it symbolically as well. So one question is like, as these numbers change, how does the value of the amount of money to put in the safe asset and risky asset change? So now that we have a formula, it's pretty straightforward to see, right? So a higher value of lambda, which would remember mean that you are more risk averse, would result in a lower value of a W star. You can see that from this formula here, right? And if you plot it, which is what we again encourage you to do, keep changing lambda numerically, then you should see that you will get a very interesting curve when you have got this, decreasing. It will probably look something hyperbolic. Then you have got this sigma b square, right, which is the risk from the risky asset, right? As it goes up, then again, as you would expect, that you want to put in less money, everything else remaining the same in this asset, right? And if your excess return is going up, then you want to put more money in this, right? So these are again things that we encourage you to plot as well, just to see numerically how it looks like. And this is something which is very useful when you're not just solving a problem, but you are understanding the solutions. But I think, Sorish, we are running out of time. So maybe we can just give a quick look ahead about how we are going to kind of like, move forward from.
Correct. Yes, absolutely.
So, yeah, do you want to take this?
Yeah. So, right, I mean, currently we are looking into the two assets, like what is there right now that we are handling as a sort of a scalar weight. We can manage it with the scalar weight, but when we will go to the many assets, we have to handle it as a vector. Then in two asset case class, we can handle the variance as a scalar variance. But when we will handle the many assets, like 10 assets or 20 assets, we have to handle it. The scalar variance will convert into variance covariance matrix.
Right. So whatever we had sigma b square, that's not going to be enough. You first need like the variance for each of the assets, but you also need to know how
The
do the risky
covariance,
assets relate to each other.
correct, how they are correlated. So that is going to play a huge role.
Right.
Then reason right now we have showed you that okay, substitution method gives you solution. But when we will move to the many assets, substitution will not be working. Only thing that will be working is the Lagrangian methods and the linear algebra method. So we have to take the help of linear algebra. And right now you can solve it by hand. It is good to start with, and then eventually many asset we for the many even more than two asset. As soon as we move to the more than two asset, three asset, four asset, five asset, we have to use matrix solver. We cannot do it by hand. It goes little difficult.
Right.
So
So I think the general point is we will generalize a lot of these concepts, and that will
correct,
introduce us to more new tools and more new computational issues that
correct,
we have to solve, right?
correct.
So I think, yeah, just some of the things that we want to generalize is rather than looking at the objective function as a just mean variance, we would want to kind of like have more general functions. Then the question is like, how do you deal with that sort of issue? So
Hmm.
these are again some of the broader questions in the course, and already I think we have kind of like outlined the basic kind of like issues, illustrations of basic issues that we are going to be dealing with. And these are some questions that I think we are going to kind of come up, and we are going to also have the tools to look into these issues as well.
Correct. So, so questions like if rate moves, how much does the bond price changes? That connect to the bond pricing formula. Then given the bond price, what yield does it imply? That connect to inverse pricing or iterative root finding methods. Then what is an option and what should it cost? That goes beyond
That's
bond
our third finance object that we'll
finance
introduce.
objective. When with 10 risky acid, how do you choose? That is a full Markowitz covariance matrix techniques. What if asset prices are themselves random? That moves us to the understanding of stochastic process. And when can we trust computational answers? Because we will be using a lot of computational technique, and that is where we have to understand the ill conditionings and the different issues of linear algebra tools. So it is going to be a really busy weeks going ahead for us. Um, the habit is the worth building to starting now, that hold a question until you have the tool to answer it well.
Right. So, okay. So we are going to continue with this over the next few weeks, and we'll
Absolutely.
also have some problem solving videos, I think, that will help you to
Yes,
internalize some of these concepts that we have studied over this.
correct. Correct. See you next week. Take care.